All right, good morning. So in the previous class, we wrapped up our discussion on sequences, and we moved on to convexity and convex sets. Right? So we saw various properties of sequences and different notions of infinities. In particular, we saw that not every sequence needs to have a limit, but then every sequence always has a well-defined lim sup and a lim inf, and the kind of results that we want to show in information theory are that we want to design good codes such that the lim sup of the rate of our code is at least a certain amount, which is close to capacity or some notion of capacity, and the lim sup of the probability of error is equal to 0. Right? So it's okay even if we cannot find a good code for every n. What we will aim for is that there is at least some subsequence of over n such that we get the parameters that we design. Okay, and in fact, I mean, so these are the results we will prove, but then you can construct codes which work for all sufficiently large. All right, so please go through the notes. This has some more material than what was covered in the class. In particular, some definitions of neighborhoods and limit points. These are all kind of technical definitions, and although it may seem very abstract, it's information that you should know. All right, so. We moved. So, any questions regarding sequences or limits?
Oh, hello, sir.
Yes, Shantanu.
Sir, I have a general doubt. Sir, like if there's a variable x and it is a line between b minus epsilon and b, so the lower limit is b minus epsilon, and
Just one sec. Let me try to write it down. Okay, so you have a sequence, is it, or a set?
sir, like I'm just taking a variable for now, like as x for example.
Okay, is it a random variable or a deterministic?
Deterministic.
Okay, so it's some number, right?
Yes, sir. And it lies between b minus epsilon and epsilon for some epsilon greater than 0.
Okay.
So can I say that by assuming only this, that x tends to b?
No, right? I mean, it's one number, right? So there could be some epsilon such that
So the limit of x tends to b.
So x is one number, right? So either it has to be a sequence for you to say that it tends to something, or it has to be a function.
Yes, it tends to be a sequence, correct? Yes.
Right. So b minus epsilon and b plus epsilon. So therefore, it must mean that the limit of this function f of x as x tends to some number a is equal to b.
Yes, sir. Got it.
Right?
Yes, sir.
So for a single number or a single variable, it doesn't make sense to say that x tends to be. Of course, you can always say that the limit. This is of course a trivial statement, but the limit as x tends to b of x, this is equal to b. It's not carrying any useful information.
Yes, sir.
Okay. Any other questions? All right.
Sir, am I
Yes,
audible?
yes.
Sir, is it like we have proved that? I mean, we have said that the rate regions are convex, and we said that like assuming TDMA, that is alpha fraction of time for user one and 1 minus alpha for user two, we said that we can form like we said that it is convex. But is it like only through TDMA we can say that it is?
No. So I'll discuss that in a little bit of detail now. But it is not really uh, TDMA, but it's a slightly more general concept called time sharing. I'll come to that in just a minute.
Okay, okay, sir.
Okay. Okay.
Okay,
Fine.
sir.
So
Thank you, sir.
all right. So right. So in the last class, we've also defined these notions of open and closed sets, and more importantly, what a convex set is. So a set is said to be convex if you take any 2 points within the set, then the straight line joining the two also lies in the set, right? And and of course, as Shivamani pointed out, what we want to show is that if you look at the achievable rate region, which is the set of all R1, R2 up to RL, for which you can construct codes with rates close to R1, R2, RL, and the probabilities of error are all vanishing in N. So the set of all such achievable rates is convex, okay, or the rate region is convex. Okay, so just a quick recap as to what the problem is. The problem is the following: we have n transmitters, each of which have a separate message. So M1, M2 up to ML are all separate messages. Uh, each message consists of ki bits. So the ith message consists of ki bits. So the transmitter 1 wants to send k1 bits to receiver 1, transmitter 2 wants to send k2 bits to receiver 2, and so on. Right? So for this problem, we want to know in the limit what is ki over n. Right? So remember that each ki is a function of n. So as n increases, the number of information bits that you transmit will also increase. So we want to know what is the limit of reliable. So in the limit as n tends to infinity, what are the rates that we can achieve while also simultaneously satisfying the property that the probability of error is vanishing in n. All right, and so our goal is to understand the properties of these rate regions, and the claim that we made was that rate regions are convex. Okay, so any rate region, not just for the problem that I have defined over here, but even if you have, say, a multiple access channel, or even if you have a broadcast channel, any such channel for which the channel behaves in a memoryless fashion, always uh, satisfies the property that the rate region is convex. Okay. All right, and so let's see, and I gave a high-level overview of what the idea is, and the idea is the following: it is an argument called time sharing. So the argument is the time sharing argument, and basically it is the following. So you know that. So let us take any 2 points in the rate region. Okay, so let us, for simplicity, let us assume that there are two transmitters and two receivers. All right, so basically two messages are to be sent, and let us say that the rates R1, R2, and rates R1 prime, R2 prime are achievable. Okay, so these are 2 points in the rate region. So what does this mean? This means that there is some subsequence such that for all sufficiently large n, so you can transmit kn bits. So transmitter 1 can send kn of 1 bits, transmitter 2 can send kn of 2 bits, and each of these so kn of 1 is at least r1 times n plus epsilon, and sorry, let me get it a bit more formal. Yes, any questions? R1 minus epsilon, and K2 is at least n times R2 minus epsilon. So fix any epsilon, you know that you can at least transmit these many bits in n uses, and this holds for all sufficiently large n. All right. So similarly, there is some. Okay. So there is an encoder, decoder for both transmitters and receivers, which satisfies this. Similarly, there are also encoders and decoders such that kn of 1, let me call it kn prime of 1, is at least n times r1 prime minus epsilon, and k2 is at least n times r2 prime minus epsilon, right? So for all sufficiently large n, you can transmit at least nr1 minus epsilon bits, and transmitter 2 can transmit nr2 minus epsilon bits. So there is one encoder which does this, and there's another encoder, an encoder decoder, which achieves the following, and this holds for all sufficiently large n. Okay. All right. So this is good. So what we want to show is that alpha r1 plus 1 minus alpha r2, sorry, 1 minus alpha r1 prime, alpha r2 plus 1 minus alpha r2 prime. So these rates are also achievable. So there exists some encoder decoder which gets you to this rate for sufficiently large n, right? And the basic idea is the following. So you have n channel uses. Okay. In n channel, I'll split the n channel uses into two parts. So in the first alpha n channel uses, I'll use this encoder decoder. I will use this encoder decoder pair. So transmitter 1 use encoder 1, decoder 1, and transmitter 2 uses transmitter receiver 2 use encoder 2, decoder 2. Okay, and using this, I know that in alpha n channel uses, I can transmit how many bits? So in alpha n channel uses, how many bits of information can transmitter 1 send? If you use encoder decoder?
So alpha n k1.
Correct. So alpha n, yeah. So alpha kn of 1. So transmitter 1 can transmit these many bits, which you know is at least alpha n times r1 minus epsilon, and transmitter 2 can send alpha kn2 bits, which you know is at least alpha n into r2 minus epsilon. Okay, that's fine. So we have, so in the first alpha n uses, you use this encoder and decoder. Not that this is generalization of TDMA. In that, in TDMA, what you were doing was only one transmitter was sending in the first alpha n channel uses, and only transmitter 2 was sending in the remaining 1 minus alpha n channel uses. But now I'm saying something different. So both transmitter 1 and transmitter 2 are going to be transmitting in the first alpha n channel uses, but they're going to use one coding scheme, right? So they're both going to transmit, but they'll use coding scheme 1. So let me call this coding scheme A, and let me call this coding scheme B. All right, so in the first alpha n channel uses, you use A, you use coding scheme A.
Yes.
Yes.
So, like during the first alpha n time channel uses, so both the transmitter 1 and transmitter 2 will use the same channel, right?
Yes, they're going to simultaneously transmit in the first alpha n channel uses, but they're going to use encoder decoder A.
And they can also be in TDLA, right?
It can also be in, sorry, what?
So first alpha n channel uses,
Yes.
like that channel use can also be like TDLA type, like some fraction of the alpha n times transmitter 1 will send, and the rest of the time transmitter 2 will send.
It could be any scheme. It doesn't matter what it is.
Okay.
Right. So use any scheme which achieves rate R1, R2.
Okay.
Right. So it's completely general. Maybe in the first alpha n channel uses they use TDMA. Maybe they use something else. Doesn't matter.
Got it.
Okay, but you know that there is some sequence of encoders and decoders which allows you to transmit kn of 1 bits and kn of 2 bits respectively, right? And now, so basically, you're partitioning the message into two parts. So the first part consists of alpha kn of 1 bits and alpha kn of 2 bits respectively. And the second part will consist of the following. So in the next 1 minus alpha times n channel uses, you use the other coding scheme. Use coding scheme B. All right, so basically you use encoder prime, decoder prime. Right. So since these are sequences of encoders and decoders, they're kind of well defined for each n. Okay, and you know that how many bits can you transmit? You can transmit 1 minus alpha kn prime of 1 bits, which is at least 1 minus alpha n into r1 prime minus epsilon, and transmitter 2 can send 1 minus alpha times kn prime of 2 bits, which is at least 1 minus alpha n into r2 prime minus epsilon. Correct? So far is it clear?
Yes, sir.
Okay. Right. So this is so basically, what is the total number of bits that transmitter 1 is sending in n channel uses? It is alpha kn of 1 plus 1 minus alpha kn of 2. So this is the total number of bits that transmitter 1 is sending. Total number of message bits.
It should be 1 minus alpha kn dash 1, right?
Sorry, kn of right. Tx1 is alpha kn of 1 plus 1 minus alpha kn prime of 1 which you know is at least n times alpha r1 plus 1 minus alpha r1 prime minus epsilon. And similarly, the total number of message bits sent by transmitter 2 is alpha kn prime of alpha kn of 2 plus 1 minus alpha kn prime of 2, which is at least n times alpha r2 plus 1 minus alpha r2 prime minus epsilon. All right. So, and this holds for every epsilon greater than 0, and therefore the rate that you can achieve is at least alpha r1 1 plus 1 minus alpha r1 prime and alpha r2 plus 1 minus alpha r2 prime. Okay, so this much is fine, but there is one more tiny detail that is missing over here. Can anyone point out what that is? So we've shown that the rate that you can achieve using this time sharing scheme is at least alpha r1 plus 1 minus alpha r1 prime, alpha r2 1 minus alpha r2 prime. Is this enough, or do we have to show something else?
We need to show the probability also holds true.
Correct. So you need to also show that the probability of error is vanishing in n, right? Because I've now considered two. So I have two schemes, and I've taken a convex combination of the two schemes. I've shown that the rate or the number of information bits that you can transmit is what we want. But the one last step is that we also have to show that even with this new scheme, the probability of error is also small, right? But again, that's not too hard because we demand that the probability of error is vanishing in n, right? So the overall probability of error, just using the union bound, is at most the probability of error that you get in the first alpha n channel uses plus the probability of error of in the next 1 minus alpha n channel uses, right? So this will be some, let me call it beta n. Let's suppose that the probability of error is beta n for n channel uses. It will be some function of n. Let's call it beta n, and or let me call it beta alpha n. And the second scheme is going to give me a probability of error beta prime of 1 minus alpha n. So both of these are such that the as for sufficiently large n, beta alpha n tends to 0, and for sufficiently large n, beta prime 1 minus alpha n also tends to 0. So therefore, and therefore the sum will also tend to 0. Right? So it's basically just a union bound argument. Right? So any questions? So basically what we showed was that suppose you have any two schemes, one which achieves a rate R1, R2, and another scheme which achieves R1 prime, R2 prime, then we can always construct another scheme which achieves alpha R1 plus 1 minus alpha R1 prime and alpha R2 plus 1 minus alpha R2 prime. So any scheme, any rate which is on the line joining these two rates is also achievable. Right, and therefore the rate region is convex. Now, there's one thing to keep in mind. It's a minor detail, but suppose you have these two schemes. So this is scheme A and scheme B. All that we've shown is that there is some scheme which achieves a rate point in the line joining the two. Okay, it is not necessarily the best scheme in the sense that suppose you design a scheme for to achieve rate point A, and it achieves the least probability of error, whatever that is. Okay, and there's another scheme which achieves the least probability of error for this rate. Now, this time sharing scheme is not the best in terms of achieving the least probability of error. There could be some scheme which does better, because after all, in a time sharing argument, you're using a convex combination of these two. You're using scheme 1 for the first alpha n channel uses, and scheme 2 for the next 1 minus alpha n channel uses. So the probability of error is not really the best that you can achieve, but that's fine. We don't care, or we're happy as long as the probability of error is vanishing in it. So therefore, it is not the best in terms of the probability of error, but in terms of the rate that you can achieve, it's good enough. Right? Any questions? Note that the TDMA is a special scheme, a special case of this, where the point 1 or point A was basically this point where user 2 would only user 2 would transmit, and point B was when only user 1 was transmitting and user 2 remained silent, and TDMA gets you any point along this line. Okay, and we've shown a generalization where you can take any two sets of encoders and decoders, or any two different schemes, and that gets you any point in between the two. Right. So time sharing is a general argument used in multi-user information theory, and it's a useful thing to know. Okay. All right. So with this, we'll sort of closely wrap up the discussion on convexity. There's a little more. So all of this was the topics from. So this was something new. What you just saw on time sharing and the convexity of the rate region. Note that this. If you think about it carefully, this is fairly general, and it holds not just for the kind of setups that is indicated over here, but also for, say, the multiple access channel or the broadcast channel. But there was one property that we used. So for the time sharing argument to hold, for all the arguments that I made over here, one assumption or one hidden assumption that was made was that the behavior of the channel in alpha n channel uses and the behavior of the channel in the remaining 1 minus alpha n channel uses are independent, and they're identically distributed. So this holds for all memoryless channels. The time sharing argument holds for all memoryless channels. But then if there is memory, then you cannot. Then this particular argument does not go through. So then a similar time sharing, an identical time sharing argument does not hold. So time sharing for any memoryless channel. So it can have multiple users. All of that is fine, and it's very general. But the key assumption is that the channel is memoryless. So the behavior is identical, and it's independent across the channel users. Okay. For channels with memory, So for example, if you have a frequency selective fading channel, then then the time sharing argument does not go through directly, but there are tricks that you can play. As long as the dependence across channel use is not too much, you can always do some kind of a padding in between to make sure that the first block is independent of the second block and so on. But that's a different story. All right. So now that we've defined what convex sets are, we also want to know what a convex function is. All right. So can someone tell me what is the definition of a convex function? So let's look at any function from R to R. So when is f said to be convex?
For any t or alpha which lies between 0 and 1,
Okay. What
that
happens?
should be satisfied the condition
Uh-huh.
that f of alpha of x1 plus
Alpha
1 minus
x1.
alpha of x2
Uh-huh.
should be less than
Okay.
or equal to
Less than or equal to?
alpha times f of x1 plus 1 minus alpha times f of x2.
Okay. All right, that's good. So if for all alpha between 0 and 1, and for all x1, x2, the following holds, that f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. And if you look at it geometrically, then basically it is the following. You take any 2 points, x1 and x2, then this is f of x1 and this is f of x2. If you look at alpha x1 plus 1 minus alpha x2 plus 1 minus alpha x2, then it lies in the interval between x1 and x2. So f of x1 plus 1 minus alpha x2 lies over here. All right. So this point lies over here, but then alpha f of x1 plus 1 minus alpha f of x2 lies on the line joining these 2 points, and therefore would lie somewhere over here, maybe over here. Right, and just by looking at this picture, it is clear that f of alpha x1 plus 1 minus alpha x2 should be less than or equal to alpha f of x1 plus 1 minus alpha f of x2. And in general, this definition of convex functions can be generalized. So as long as A is a convex set, of more generally Rn, then any function from A to R is convex if the following holds, right? So if you look at it again, if you try to visualize what is happening, then a convex function has to look something like a bowl, and you know, and f of alpha x1 plus 1 minus alpha f of plus 1 minus x2 is going to lie somewhere on this bowl, whereas alpha f of x1 plus 1 minus alpha f of x2 is going to lie on sort of a plane. Think of it like a plate covering this bowl, and therefore that's always going to lie above the bowl, right? And similarly, you say that f is concave if it's like an inverted bowl. So if minus f is convex. All right. So what can you say about these functions? X square, is it convex or concave? Right. So f is so x square is convex. What about, let's say, e power x? So is e power x convex or concave?
Convex.
It's convex, right? What about log x?
Could be concave, sir.
Yeah, it's going to be concave. All right. So think about all of these functions. So it's good to know which of these functions are convex and which of them are concave, because we'll be using them later on. All right. So one test for whether a function is convex or concave is the following. So it's by evaluating the second derivative. So f from R to R is convex. So suppose that both the first and the second derivatives of f exist. Then when do you say that this is convex?
If it is greater than 0.
Correct. So it's greater than or equal to 0. So it's convex if it is greater than or equal to 0. So there's also a stronger notion of strict convexity. So it's strictly convex if this inequality is a strict inequality, and equality holds only when alpha equal to 0 or 1. Right? And similarly, it is strictly convex if f double prime of x is strictly greater than 0 for all x. All right, and okay, and it's concave if it's the other way around, if f double prime of x is less than or equal to 0. Okay, so one key property of convex functions is the following. So convex functions satisfy Jensen's inequality, and it says the following. So if you have a function, a real valued function which is convex, and you take any random variable x, then f of expectation of x is less than or equal to expectation f of x. All right, and using this you can prove the logs of inequality, which says that if you have a1, a2 up to an, which are non-negative numbers, and b1, b2 up to bn, which are also non-negative numbers, then the sum of ai log ai by bi is always lower bounded by summation ai log summation ai over summation bi. So I won't discuss this in detail, since this was already covered in the information theory or information sciences course. So you can go through your notes to refresh yourselves on these particular topics. This is also covered in the textbook by Cover and Thomas. I think it's in chapter 2, if I recall. All right. So any questions regarding these topics? Okay, so we've discussed both sequences and convex sets in a fair amount of detail, and that covers a lot of the preliminaries that we need. So we'll go to the last topic in the preliminaries part. We'll talk about some concepts in probability, and then we'll go to the actual heart of the subject. We'll start talking about information theoretic concepts. All right. So these concepts in probability are very, very important, as we'll be using these a lot in the course. After all the systems that we will analyze are random in nature. So it's good to have a strong foundation in probability. Now, some of these, again, as in the previous case, some of these concepts will have been covered in a basic course in probability, but then there will be some new concepts as well. So we'll start off with something very simple, and that is that the following union bound, which you've seen multiple times, and is used very, very frequently in solving many kinds of problems. And that is, if you have A1, A2 up to AK, if you have multiple events, then the probability of the union of these events is upper bounded by the sum of the probabilities of the individual events. All right. So, for example, if you have if you are, say, rolling a die, and event A, let's say that event A1 is the event that you get either 1 or 3, and event A2 is that you get either 3 or 4, then the probability of a union of these two events, 1, 3, 4, is upper bounded by the probability of 1, 3 plus the probability that you get either 3 or 4. Now, in general, the union bound is weak. So it's not a very good bound, but it is almost always very convenient, because in many situations, the probabilities of the individual events A1, A2, and so on, but finding the probability of the union can be very, very complicated. Right? So typically, when we analyze, say, probabilities of error, one very common trick used both in communications and information theory is that when you want to find the overall probability of error, you first try to find what is the pairwise probability of error. You can find what is the probability of confusing one point with another point, and that's fairly easy to calculate. But then when you want to find the probability of error for the entire constellation or the entire code book, it becomes much harder. So what you do is you just take a union bound. So the probability of the overall probability of error is the sum of the pairwise probability, is upper bounded by the sum of the pairwise probabilities of error, and that is something that is much easier to analyze. All right. So that's the first concept. So another sort of broad class of concepts that are very useful are concentration inequalities, and that is, given a particular random variable, you want to know what is the probability, or what upper bounds on the probabilities that the random variable lies in a particular set. Okay. So and the most basic inequality that you would have also seen in your probability course is Markov's inequality, which says that if x is a non-negative random variable, then for any number greater than 0, any number a greater than 0, the probability that x is greater than or equal to a is upper bounded by the expectation of x divided by a. All right. So it's a very simple inequality. And here's a proof. You can go through it later. It's a very simple inequality, but it also forms the foundation of many other inequalities that you can prove. So in particular, you have the Chebyshev inequality, which says that if you have any random variable x which has a finite mean and a finite variance, then the probability that x deviates from the mean by an amount of alpha is at most the variance of x divided by alpha square. Okay, and the way to prove Chebyshev's inequality is to apply Markov's inequality on a suitable random variable. So essentially, almost all such inequalities that you can prove all boil down to using Markov's inequality on a slightly different random variable than the one that you have. So in this particular case, to prove Chebyshev's inequality, you will apply Markov's inequality on the random variable x minus expectation of x, the whole square. So you basically get this by squaring both sides. And so probability that mod x minus expectation of x is greater than or equal to alpha is the same as the probability that x minus expectation of x, the whole squared, is greater than or equal to alpha square. And just applying Markov's inequality to this statement gives you expectation of this random variable, which is equal to the variance, and divided by alpha square. All right. And similarly, you can derive an another inequality, which is the Chernoff bound. So the probability that any random variable x with well-defined moments, so the probability that x is greater than or equal to alpha can be upper bounded by expectation of e to the t times x divided by e to the t times alpha for all t greater than 0. Similarly, you can have the following bound: the probability that x is upper bounded by some quantity beta, which is at most e to the t times beta times expectation of e to the minus tx. Okay, so have you seen the Chernoff bound previously in your courses? So you would have seen this in the information theory or information sciences course, hopefully. But was this covered in a probability course? So is there anyone who has not seen the Chernoff bound before? Okay, so hopefully you've seen this. Okay. All right. So in this course, we're typically in yeah. So what is more useful is the so-called a simplification of the Chernoff bound. So Chernoff bound is fairly strong, but in many cases it is very difficult to evaluate. So basically, to find a good enough bound, note that this holds for every t greater than 0. So therefore, the probability that x is greater than or equal to alpha is less than or equal to the minimum overall t greater than 0 of expectation of e to the tx divided by e to the t alpha. Now, computing this bound is generally hard, but at least for Bernoulli random variables, so in particular, if you have x1, x2 up to xn, which are IID Bernoulli P, this can be simplified. So the probability that the summation of the xi's, that each xi is IID Bernoulli P. So by Bernoulli P, I mean that the probability that xi is equal to 0 is 1 minus p. Of 0 is 1 minus p, and the probability that xi is equal to 1 is equal to p. So if you have IID Bernoulli random variables, then you have the following nice upper bounds. So the probability that that the summation overall xi deviates from the mean, which is equal to np by an amount n delta, is upper bounded by some quantity which is exponentially decaying. So this is a very, very useful bound, and we'll make use of this in the next couple of classes. All right. Now there are many other. So this is what is called a concentration inequality, and it is so called because what this statement basically says is that the summation of all the xi's, when xi's are IID Bernoulli P, this is highly concentrated about the mean. So the probability that it deviates from the mean by even a small amount, by n delta, is exponentially decaying. Right? And there are similar concentration inequalities that you can prove for more general random variables. So in particular, for any sequence of bounded random variables, which are all independent and not even necessarily identically distributed, you can prove a similar result. So you can prove that the summation is very close to the mean, and the probability that it deviates from the mean also decays exponentially in it. And this is given by the so-called Herfding's inequality. And you can generalize this not just to sums, but more general functions with certain properties. So in particular, functions which satisfy what is called a bounded difference property. And you can prove a similar exponentially decaying bound for such functions of random variables. And that's given by the McDermott's inequality. So we won't be using these two inequalities so much in the course, but these are useful tools to know. And in particular, if you're doing any kind of work in statistical inference, machine learning, or even information theory, there will be many other problems where these inequalities are more suited. All right. So in particular, all of these correspond to sequences of random variables, but finite sequences of random variables. But what we want to understand are also infinite sequences of random variables. So all of these, so suppose that you have a sequence, so just as we saw real valued sequences or complex valued sequences, we're also interested in studying sequences of random variables and what it means for a sequence of random variables to converge. Now, of course, you would have seen, you've already seen convergence of sequences of deterministic quantities. So you know what the limit is, we've seen what the lim sup is and what the lim inf is. But when you have a sequence of random variables, it is not clear what is meant by convergence. And in fact, there are different notions of convergence, as we'll see in a minute. So in general, you can have a sequence x1, x2, x3, so an infinite sequence, and these need to be specified by some joint distribution. So they could be independent and identically distributed, which you've seen in the information theory course. So any sequence of random variables is specified by the finite dimensional distributions. Which basically says that for every subset of random variables, I to ik, the joint distribution needs to be well specified. Pxi1, xi2, up to xik needs to be specified for all subsets I1, I2, up to ik. Okay, and in particular, if you take any finite set of random variables and they are independent and identically distributed, then we say that the sequence is independent and identically distributed. So this sort of captures random variables which are memoryless. So whenever we talk about memoryless systems, we're essentially talking about IID random variables. And similarly, the simplest form of dependence is captured by a Markov chain. So in other words, in the sequence, every random variable in the sequence depends only on the k previous random variables, and given the k previous random variables, it is independent of everything else. So xi so conditioned on xi minus 1, xi minus x2 up to xi minus k, the random variable xi is independent of everything else in the past. So by the past, I'm talking about x1, x2 up to xi minus k minus 1. Right, so this is what we call a Markov chain, and we will exclusively focus on IID and Markov chains in this particular course. Right, but many of these statements can be generalized to more general, what are called stationary sequences of random variables. So we say that a sequence of random variables is stationary if you look at any locations I1, I2 up to ik, then the distribution of xi1, xi2 up to xik is the same as those locations shifted somewhere in the past or the future. So the distribution of xi1, xi2 up to xik is the same as the distribution of xi1 plus m, xi2 plus m, xi3 plus m up to xik plus m for every shift m. Right? So this is what we mean by a stationary sequence, and this is essentially a stationary random process which you would have studied in your course on random processes. So given any such random process which is stationary or IID or Markov, we want to know what it means by the sequence of random variables to converge. So you have a sequence of random variables, maybe these correspond to the channel, or maybe these correspond to the encoders and decoders, or maybe it's even the probability of error, which could be a random variable depending on how you define it, and you want to know how it behaves in the limit. So for sufficiently large n, what happens to the sequence of random variables? Okay, and unlike deterministic sequences, it's the concept of convergence of random variables is slightly more nuanced. So since we're out of time, we will discuss this in our next class. But what I want to know is, have you seen these convergence of random variables in a previous course? Have you studied it in your probability or random processes course? How many of you have not seen? How many of you don't know what is almost sure convergence, or convergence in probability, or convergence in distribution? Has anyone not seen these concepts? I just want to know whether this was covered in a previous course or not. Okay, so Suhit Kumar says that he has not seen it. Girish has also not seen it. What about the others? Have you seen it? So is this typically covered in a course in probability or random processes?
Sir, is it regarding this weak law of large numbers and all?
Generally, yes. So have you seen this in a course?
Yes.
Okay, so you've seen almost sure convergence and convergence in probability in that course?
I think only weak law of large numbers was discussed. I thought that only is the convergence. So almost, I mean, if there is some definition, then I'm not sure, sir.
Okay, sure. It depends on how it was sort of defined. So have you seen the strong law of large numbers?
Yes, sir.
Okay. Yes, Suman?
Yeah, so what I was thinking, we know about that weak law of large number and strong law of large number, but like we have seen these terms and this almost sheer, like convert almost purely or convert this problem, but it will be good if you just go to it a little bit deep. Then that concept will
Sorry,
be clear.
I can't hear what you're saying.
So what I'm saying is, even if we for the concept, we know the term, it will be good if you just describe in a little bit detail. So that
Sure. I will cover this. But yeah. Anyway, there are some people who have not seen this at all, so it's good to do it. Again, I will not be proving statements, but I will certainly define all of these, and you'll see some examples as to what it means to converge in probability, in distribution, and almost surely. Okay, so let's wrap up for the day. We'll meet again on Monday. But yeah, if there are any questions, you can ask them now. Okay, so a reference for these topics. So for the topics on convexity, you can go through the textbook Elements of Information Theory by Cover and Thomas, the basic standard textbook for the information theory course. And for these notions of, so this is sort of a mix of which I've taken from various places. For these basic inequalities, you can just look up Wikipedia or any standard textbook in probability. Typically, so for example, this, yeah, so many of these are covered in, let's say, the book by Polis, I think. So which textbook was followed for the probability course or random processes course? Polis, yeah, that's good enough. So that's a good textbook. It covers most of what is required. So probably concepts of convergence and probability and almost surely, I'm not sure in what detail it is covered in Papolis, but certainly.
I think it has in Thomas and Cover book also.
Yeah, sure. That's also covered in the book by Cover and Thomas. Personally, what I learned from was from the notes by Bruce Hayek. Let me just put a link. So chapter 2 of these notes should cover what is needed. It's a good set of lecture notes. It covers a lot. Also, particularly concepts of Markov chains and so on. So did you see Markov chains in your course on probability or random processes? Are these concepts typically discussed? Okay. So was it just basic definitions of Markov chains, or did you also go through things like the stationary distribution, when the stationary distribution exists, and recurrent Markov chains and transient Markov chains and so on?
Yes, sir, but like definition kind of thing. So, sir has explained the things.
Okay, sure. Good. Okay, any other questions? Okay, if not, then we'll stop for the day.